Today we are going to design a composite floor, and the question of today says this: steel universal beams at 3.5 meters centers with 9 meters simple span are to support a 150 millimeters deep concrete slab of characteristic strength 30 newtons per square millimeters, as shown in the figure below. If the imposed load is 4 kilonewtons per square meter and the weight of the partitions is 1 kilonewton per square meter, part A of the question, select a suitable UB section in grade S355 steel. Part B, check the shear capacity. Part C, determine the number and arrangement of 19 millimeters diameter by 100 millimeters long headed stud connectors required. Part D of the question, assuming the slab is reinforced in both faces with H8 at 150 centers with area of steel 335 square millimeters per meter, check the longitudinal shear capacity of the concrete. Part E, which is the last part of this question, calculate the imposed load deflection of the beam. Assume that the weight of the finishes and sealing and service loads are 1.2 kilonewton per square meter and 1 kilonewton per square meter respectively. The density of normal weight of reinforced concrete can be taken as 24 kilonewton per cubic meter. So let's see how we go about this question. I am George Kamiti and welcome to our today's lesson. The depth of the concrete flange is 150 millimeters. The characteristic strength of concrete is 30 newtons per square millimeters. The characteristic strength of steel reinforcement is 500 newtons per square millimeters. The imposed load is 4 kilonewtons per square meter. The partition's load is 1 kilonewton per square meter. Stud connectors, shank diameter 19 millimeters by 100 millimeters high. The area of bolts 335 square millimeters per meter. Load of finishes 1.2 kilonewtons per square meter. The sealing and service loads 1 kilonewton per square meter. The density of concrete 24 kilonewtons per square meter. Beam span 9 meters and slab span 3.5 meters. We are going to begin with calculation of design moment, which will help us or guide us in selecting a suitable beam section. Therefore, starting with part A of this question, that is beam selection. Beam selection. And under beam selection, we are going to begin with calculation of design moment. Therefore, we go to calculation of design moment. And in this case, we are first of all going to determine the design load per beam. So we go to, that is how they will follow each other, design load per beam, that is W. Therefore, the design load W per beam will be given by 1.4 into depth of the concrete flange times the density of concrete plus load of all the finishes plus load of sealing and services, and then we multiply by the slab span, that is L. This one we are going to add it to 1.6 into the imposed load that we have been given, that is QK, 4 kilonewtons per square meter. We add partition rods, so plus partition loading, and then we multiply by slab span, that is L of 3.5 meters. Remember, we usually have this formula when we are calculating the design loading, which is usually given by 1.4 GK plus 1.6 QK, where GK denotes dead load and QK denotes imposed or live loads. And therefore, all these are dead rods, finishes, sealing, services, all those are dead rods, whereas partitions, those ones are live loads. Therefore, our design load per beam will be given by 1.4 into the depth of the concrete flange is 150 millimeters. We convert to meters. We divide 150 by 1,000, and that is going to give us 0.15 meters. We multiply by the density of concrete, which is 24 kilonewtons per square meter. Then we add the load of finishes, which is 1.2 kilonewtons per square meter. Then we add the load of sealing and services, which is 1 kilonewton per square meter. And then we multiply this by the slab span, which is 3.5 meters. Therefore, multiply by 3.5 meters. Then we add these two, 1.6 into QK. The imposed load is 4 kilonewtons per square meter. We add partition loading, which is 1 kilonewton per square meter. And then we multiply that by the slab span, which is 3.5 meters. And therefore, when we do so, we are going to get a load, a design load of 56.4 kilonewtons per meter. 56.4 kilonewtons per meter. Therefore, that is the design load per beam. Then from there, we are now going to calculate the design moment. And therefore, the design moment, that is M, will be given by WL squared divided by 8. We treat the beam as a beam carrying a uniformly distributed load over its entire span. And therefore, this will be equal to W, the design load, 56.4 kilonewton per meter, times the beam span, which is 9 meters. Therefore, that is going to be 9 squared, divide this by 8. And by doing so, we are going to get a design moment of 571 kilonewton meter. Therefore, that is the design moment. From there, we are going to determine the effective width of the concrete slab. So we go to calculation of effective width the concrete slab. Concrete slab. And the effective width of the concrete slab will be given by the lesser of the two. One of them is the beam span divided by 4. And the beam span in this case is 9 meters. Converting it to millimeters, that is multiplying 9 meters by 1,000 to give us 9,000 millimeters. Therefore, the beam span will be 9,000 millimeters. We divide by 4. And that is going to give us 2,250 millimeters. 2 will be the beam spacing. And the spacing of our beams is 3.5 meters center to center. So converting 3.5 meters to millimeters, that is going to give us 3,500 millimeters. Therefore, the lesser of the two is 2250 millimeters, which we are going to use as our effective width. And therefore, the effective width is going to be 2,250 millimeters. Therefore, that is the effective width of the concrete slab. From there, we are now going to calculate the moment capacity. Therefore, we go to calculation or determination of moment capacity of the beam. And the moment capacity in this case, first of all, we are going to use trial and error method to select a suitable beam section, which we are going to use in our calculations. And in this case, using trial and error, we are going to try this beam section of serious size 356 by 171 by 45 universal beam section. Therefore, use trial and error. Try this section 356 by 171 by 45 UB section. And in this case, this particular UB section will be of grade S355, grade S355 steel section. That is what we are going to try in our case. And therefore, beginning with calculation of the resistance of the concrete flange, that is RC. Therefore, we go to calculation of the resistance of concrete flange. That is RC. RC in this case will be given by 0.45 FCU multiplied by AC. That is the area of the concrete flange. And in this case, our RC, the resistance of the concrete flange, will be equal to 0.45 multiplied by FCU, which is the characteristic strength of concrete, 30 newtons per square millimeters. We multiply that by 30 times AC is given by the effective breadth of the concrete flange times the depth of the concrete flange, that is DS. And in this case, BE, the effective breadth of the concrete flange, we have calculated here and found that it is 2250 millimeters. Therefore, we multiply that by 2250 millimeters times the depth of the concrete flange is 150 millimeters. Therefore, multiply that by 150 millimeters. We are going to get the resistance in newtons, but to convert newtons to kilonewtons, we are going to divide the whole of this calculation by 1000, or we multiply by 10 raised to the power of -3. And by doing so, we are going to get a resistance of concrete flange, a resistance of 4556.3 kilonewtons. Therefore, that is the resistance of the concrete flange. From there, we are going to determine the resistance of the steel beam. Therefore, we calculate the resistance of the steel beam. And in this case, that is denoted by RS. And RS is given by A multiplied by PY, whereby A is the area of the selected beam section and PY is the design strength of steel. And in this case, our steel is in grade S355, meaning that the design strength of our steel is 355 newtons per square millimeters. Therefore, PY, the design strength of our steel section, is 355 newtons per square millimeters. Therefore, the resistance of the steel beam RS will be equal to the area of this steel section from appendix B of the UB of BS 5950 is 57 square centimeters. So we convert 57 square centimeters to square millimeters. So we are going to multiply 57 square centimeters by 100, which will give us 57 times 10 squared square millimeters. Remember, 1 centimeter is equivalent to 10 millimeters. Therefore, when you square the centimeter, you also square the millimeters. Then you multiply by 355 newtons per square millimeters. 355. We are going to get the answer in newtons, but to convert to kilonewtons, we are going to multiply by 10 raised to the power of -3, or divide that calculation by 1000. And in this case, the resistance of a steel beam, that is RS, will be given by 2023.5 kilonewtons. 0.5 kilonewtons. Good. Since RC is greater than RS, the plastic neutral axis will lie in the concrete slab. Remember, we usually have 3 cases, case 1, case 2, and case 3, whereby in case 1, the neutral axis falls in the concrete flange, and case 2, the neutral axis falls in the steel flange, and case 3, the neutral axis falls in the steel web. And therefore, when RC is greater than RS, that is the resistance in concrete flange, greater than resistance in the steel flange, the neutral axis will lie in the concrete flange. And therefore, we can prove that the neutral axis falls in the concrete flange by substituting y, or calculating the depth of the neutral axis, which is yp, that is the depth of the neutral axis. And it is given by this formula, a py divided by 0.45 f Cu multiplied by the effective breadth of the concrete flange. And in this case, the depth of the neutral axis will be equal to APY. APY, that is the resistance of the steel beam. And we have gotten it as 23.5 kilonewtons. We are going to convert that to newtons. So we multiply kilonewtons by 1,000 to convert it to newtons. We divide this by 0.45 times characteristic strength of concrete, that is 30 newtons per square millimeters, times the effective effective width of the concrete slab, which is 2250 millimeters. So times 2250 millimeters. And by doing so, YP is going to be 66.6 millimeters. And therefore, we find that YP, which is 66.6 millimeters, is less than the depth of the concrete flange, which is 150 millimeters. And therefore, that shows that the neutral axis falls under the concrete slab. Therefore, the moment capacity will be given by this formula, since YP, or the neutral axis, falls under the concrete slab. Therefore, the formula for calculating the moment capacity will be as follows. MC is equals RS into DS, that is the depth of the concrete flange, plus D over 2, that is the depth of the selected steel section obtained from Appendix B of BS 5950. Then we subtract RS divided by RC multiplied by depth of the concrete flange divided by 2, or concrete slab in this case, divided by 2. Therefore, the moment capacity will be given by RS, which is 23.5 kilonewtons. So we have 23.5 kilonewtons. We multiply by 1,000 to convert it to newtons, into DS is 150 millimeters. So 150. We add D, the depth of the steel section from Appendix B, that is 352 millimeters. We divide it by 2, minus RS is 23.5 divided by RC, which is 4556.3. 4556.3. Then you multiply this by DS over 2, that is 150, divide this by 2. So that is going to give us the answer in Newton millimeters. So to convert to kilonewtons meter, we are going to divide the whole of this calculation by 1 million, or in simple terms, we multiply by 10 raised to the power of -6. That will convert Newton millimeters to kilonewton meter. And by doing so, we are going to get a moment capacity of 592.3 kilonewton meter. Therefore, that is the moment capacity of this particular section. Now, this moment capacity should be greater than the total moment. And in this case, the total moment is given by the design moment plus the moment due to self weight of the beam, and in this case of the steel beam section. Therefore, moment capacity will be greater than the total moment, and in this case total moment will be given by the design moment, and the design moment we had calculated it somewhere, that is 571 kilonewton meter. Therefore that will be 571 plus the moment due to self weight will be given by this formula. Moment of a beam carrying a uniformly distributed load is usually given by load UDL multiplied by the span squared divided by 8. This W is the weight due to self weight of the beam section that we have selected. And our beam section have got a mass of 45 kgs per meter. So we need to convert this 45 kgs into weight. And weight is usually given by mass times the force of gravity. Therefore, the mass of our beam section is 45 kgs and gravity is usually given by 9.8 newtons per kg. So when you multiply 45 kgs times 45 kg per meter times 9.8 newtons per kg, we are going to get the weight in newtons. So we are going to have 45 times 9.8, which is the gravity. So when we multiply 45 by 9.8, we are going to get the answer in newtons. So we need to convert it to kilonewtons, and by doing so, we are going to divide this by 1,000, or we multiply by 10 raised to the power of -3. Then L squared, that is the beam span, which is 9 meters. Therefore, 9 squared divided by this 8 that we got here. And by doing so, we are going to get this part. The whole of this part is going to give us 4.5 kilonewtons. And therefore, we are going to have 571 plus 4.5, which is going to be total moment of 571 plus this 4.5, which is going to give us 575.5 kilonewton meter. And therefore, when we compare the moment capacity, which is 592.3 kilonewton meter, and the total moment, which is 575.5 kilonewton meter, we find that it is greater than total moment, and therefore the section we have selected is okay. Therefore, since moment capacity is greater than the total moment, our section that we have selected is very much okay. So that is how we deal with moment capacity. Then from there, we are going to determine the shear capacity. And in this case, the shear capacity, that is FV, will be given by WL divided by 2. And in this case, W is the design load, which is 56.4 kilonewton per meter. Therefore, 56.4 kilonewton per meter times L, which is the beam span of 9 meters. We divide that by 2. And this is going to give us a shear force of 253.8 kilonewtons. So that is the shear force of 253.8 kilonewtons. Then we are going to determine the shear resistance. So we go to shear resistance of the beam. And the shear resistance, that is PV, will be given by 0.6 PYTD, whereby PY is the design strength of a steel section, T is the thickness of the web, and D is the depth of the fringe of the section that we have selected. Therefore, the shear resistance PV will be 0.6 times the design strength of steel, that is PY 355, times the web thickness of our steel section 6.9 millimeters, that is obtained from Appendix B of the BS 5950. Then we multiply by the depth of the flange, which is 352 millimeters. Then we are going to get the answer in newtons. So to convert to kilonewtons, we are going to divide the whole of this calculation by 1000, or we multiply by 10 raised to the power of -3, since 1 kilonewton is equivalent to 1000 newtons. And that is going to give us a shear resistance of 517 kilonewtons. Since the shear resistance, which is 517 kilonewtons, is greater than the shear force, that is FV, which is 253.8 kilonewtons, then the section we have selected is very much okay. The section we have selected is very much okay. After dealing with the shear capacity, we are now going to part C of our question. This was part B, shear capacity. Part C of our question is determining the shear connectors. So we go to shear connectors. And in the part of shear connectors, from table 4.18 of BS 5950, characteristic resistance QK, the characteristic resistance QK of headed studs, which will be used as shear connectors, of 19 millimeters shank diameter by a height of 100 millimeters, QK for such studs is 100 kilonewtons. That is from table 4.18 of BS 5950. And therefore, the design strength of shear connectors, design strength of shear connectors, that is QP, will be given by 0.8 QK. 0.8 QK. And therefore, the design strength of shear connectors is going to be 0.8 times QK, which is 100 kilonewtons. And that is going to give us a QP being 80 kilonewtons. Then the longitudinal force that needs to be transferred, that is FC, longitudinal force that needs to be transferred, is 2023.5 kilonewtons, which is actually our RS. Now, since the neutral axis will fall in the concrete slab, the number of studs required, in this case are will be given by RC divided by QP. That is the design strength of the shear connectors. But our RC is going to be 2023.5 kilonewtons, which is actually the RS, since we have said that the neutral axis will fall in the concrete slab, as we discovered from this calculation here of the depth of the neutral axis. And therefore, the number of studs required will be RC, which is 2023.5 kilonewtons, divided by QP, which is 80 kilonewtons. And this is going to give us 25.3 studs. And since we cannot have 25.3 studs, we are going to approximate it to 26. We are going to have an even number of studs. Therefore, we are going to say this: provide 26 studs, provide 26 studs evenly arranged in pairs in each half span of the beam. Provide 26 studs evenly arranged in pairs in each half span of the beam, meaning that half span of the beam, we are going to have 26 studs which are evenly arranged. Therefore, the spacing of the studs will be given by half span of the beam. The total span of the beam is 9 meters. Half span of the beam will be 9 divided by 2, which is 4.5 meters. We convert that to millimeters, which is going to give us 4,500 millimeters. Then we divide by 12 studs so that we can get the spacing of the studs. Why 12? Because if this is a beam section, this is a beam section. On each side of the beam, we are going to have one pair of studs, one pair of stud. So we are going to have a stud on this side and a stud on the other side. Therefore, this side we are going to have 13. That is a half span of the beam, and the other side we are going to have 13. Now, for us to get the spacing, if we have 13 studs, we are going to divide by 12 because we have 12 spaces. In the 13 studs, we have 12 spaces in between them. That is why we are dividing 4,500 millimeters, which is half span of the beam, divided by 12 spaces of the 13 studs. And this is going to give us a spacing of 375 millimeters. 375 millimeters, which we can approximate it to 350 millimeters for just simple reasons. Therefore, the spacing will be equal to 350 millimeters center to center. 350 millimeter centers. So that is how we deal with the shear connectors. Those are the number of shear studs required, and that is how they are going to be spaced.